This is a recent trace fossil, recording the once physical presence of a living organism. As with other trace fossils, and indeed perhaps the more familiar body fossils, in the unravelling of the detective story of evolution, the challenge they throw out to us is interpretation. Find out how I once was built, worked and lived. Or, with trace fossils such as this one, the more formidable question of what left these marks, these traces of activity. What interpretation would some future paleontologist make about these marks? Would he have constructed these events, the two-legged invasion of the moon?
Wait a minute. What? Where are the reflections? I've been fooled once. There is orange soil. You can see this in your colored television, I'll bet you. And we've covered 19.3 kilometers, Jack. Stand by, but we've been everywhere we planned to go, so we must have gone just about as far as we planned to go. 99, proceeded, 3, 2, 1.
When the astronauts departed, they left behind them, visible through the window, the tracks and traces of their activity and the remains of their equipment. But would a future paleontologist know where to look if he wanted to tell the whole story of this lunar invasion from its origins, as it began millions of years ago on nearby Earth? Grand Canyon, here seen by satellite, that mile-deep gash in the Earth's crust, is an ideal place for that story to begin. From top to bottom, it's a great calendar, 1,200 million years old. The layers of rock represent sediments that were laid down and in time compressed to form this great calendar. Down here, where the Colorado continues to erode, it has laid bare rocks which belong to the Precambrian. Originally laid down as sediments in some ancient sea, they have survived Earth movements and remain level and undisturbed, and so they offer us the chance that the fossils of organisms will have similarly survived, a record of evolution of the life those seas once contained. What were these seas like? Were these Precambrian seas so very different from those of today? And do we find records of currents or wave action, and of the organisms which lived in those seas? If we can, then we will have clues as to the extent of evolution. Well, there's no shortage of fossil beaches, and we have one piece here. It has a piece of its history frozen. These ripples were formed by a current moving over the seabed. But there's something extra I want to tell you about this seabed. How were these ripples preserved? What happened was that some more sandstone was deposited on top as this layer here, so that originally the rock was found like this. The geologist then split the rock along this crack here, revealing the ripples of the seabed, but also the counterpart, a negative impression of these ripples. This is an important point which I shall return to later when I'm talking about trace fossils. Well, if you have remains of the sea preserved, their activity such as currents and waves, we should also expect the remains of organisms. And indeed this is what happens. But here we're to talk about early Metazoan evolution. It would be best if we had body fossils, but these are very rare, whereas the trace fossils are comparatively common. Now, trace fossils tell us relatively little about the phylum to which the creator belonged. However, quite often we can indicate the grade of organisation. And what I've proposed to do is look first of all at the simplest metazoans creating traces, the cnidarians, which have a diploblastic grade, and then go on and look at the flatworms and their direct descendants, the mollusks and their trace fossils, and descendants whose ancestry is more problematical, from flatworms certainly, but via a more circuitous route, the mollusks and the annelids and the trace fossils they leave. The results of the evolutionary transition from cnidarians to higher metazoans, such as arthropods and mollusks, are perfectly evident in the sea today. You'll be familiar from rock pools with diploblastic cnidarians, such as sea anemones, and their free-living pelagic relatives, the jellyfish, both of them catching food without actively pursuing it. A change of lifestyle is apparent in the flatworms, which, having a bilateral symmetry and the concentration of sense organs at one end, are well adapted to being active predators. Mollusks are even more diverse. From the browsing limpet, who rarely strays far, there ranges a wealth of styles of locomotion and feeding. Similarly, the segmented annelid worms, which range from sedentary filter feeders with fine fan-like tentacles to active predators. And then finally, there are the arthropods, the crustacea, such as crabs and lobsters, those armoured tanks of the sea. As you have seen, just as the currents that swept across the sea were recorded, this is a fossilised seabed, no longer horizontal but steeply inclined, that now outcrops on a Welsh hillside, it's likely that on and in such sediments we'll find the tracks, traces, or even bodily remains of some of the ancient relatives of the animals you've just seen. Such traces have been found in the Grand Canyon, though you've got to look hard as they're rare. If we really want to learn about Precambrian life, we must travel to other Precambrian outcrops. In Australia, and notably here in the Flinders Range, made famous by the pound quartzite. Here you get a real feeling for Precambrian life, as it was preserved over 620 million years ago. What do you make of this? Well, if modern jellyfish are any guide, this circular shape must be the remains of a jellyfish. It's been called Cyclomedusa, and it left this fossil after being stranded on some Precambrian shore. Even though jellyfish are almost all water and contain no hard parts, sometimes, if the conditions are right, their remains will survive. This one has been called Morsanites. You can see easily the radial symmetry, typical of cnidarians. So, perhaps charting the early history of metazoan life is not going to be so difficult after all, though remember that animals such as jellyfish are generally pelagic and usually not as easily preserved as animals living on the bottom, that is, benthic animals. It was only when metazoans took to the bottom in search of food that bilateral symmetry developed in adapting to actively sensing the environment and seeking out food. Bilateral animals such as this one, for instance, you can see it better if its outline is picked out from front to back, were active bottom dwellers. And today, bottom dwellers of the oceans are leaving behind the remains and traces of their activity. Paleontologists ought to look just as keenly at modern processes as at the preserved remains of the past. Explore the deep sea, and you'll see similarly perplexing traces. What do you imagine made these tracks? Here, the radiating traces mark, perhaps, the furrowing by feeding tentacles of a worm living in the central burrow. Having found food, digestion eventually produces fecal coils. But can we infer what grade of animal organisation made these marks? Cnidarian, flatworm, mollusk, annelid, arthropod, even vertebrate? Go to a more accessible area, like this modern beach, and you're less in doubt. These are the worm casts and the entrances to the burrows occupied by a polychaete worm, the lugworm, Arenicola. As Arenicola is soft-bodied, there's not much chance that it will leave a body fossil, though the burrow that it makes as it pushes its way through the sand can be preserved. Such potential trace fossils then allow us to establish what grade of animal made them. Now, in this trace fossil, the entrances and exits are marked by plugs of sand, an entrance here and an exit here. If we look at this trace fossil in cross-section, we can see, as one might expect, that they are joined by this U-shaped burrow. The name of this trace fossil is Araniculites, and although it was made by some sort of soft-bodied animal, it was not closely related to Aranicola. We can see these U-shaped burrows even more clearly in this second trace fossil here. Once again, we have a U-shape and at the top entrance and exit. The soft-bodied creature which made this burrow would have probably lived around about this region of the trace fossil. However, these trace fossils were made by metazoans of a fairly high grade, something like an annelid. What about cnidarian trace fossils? Jellyfish are pelagic and could only produce trace fossils if they touched bottom. So cnidarian trace fossils will almost always be made by benthic forms. Close inspection of the structures which stud this rock reveals them to be the traces of sea anemones. This particular trace is called dolopicnus. In a vertical section cut through the trace, can you see the vertical burrow or pit which interrupts the layering of the sediment in which the sea anemone lived? Here, in this polished section, can you see that though the sea anemone has disappeared, there appears to be some particulate structure left inside? And now, if we look more closely still, you can see that these particles appear to be parts of something, not just accumulated minerals, but more about this later. This is a present-day sea anemone. It is entirely soft-bodied, though its warm water relatives secrete the calcareous external skeletons that are coral. It has a striking radial symmetry. The tentacles are always ready to catch food, approaching from any direction, and to draw it, like this unfortunate prawn, through the central mouth, into the coelentron to be digested. In doing this, the sea anemone changes shape. Now it is no longer expanded, but hunched up round the meal inside. This is possible because the anemone uses the fluid contents of the gut as a hydrostatic skeleton upon which two sets of antagonistic muscles act. A cnidarian, such as this sea anemone in section, shows how it consists essentially of two cellular layers, separated by a gelatinous matrix. This is the diploblastic condition. Within these layers lie two opposing sets of muscles. Longitudinal muscles which run the length of the sea anemone and extend into the partitions or septa that project into the coelentron, and bands of radial muscles which encircle the animal like the hoops of a barrel. Elongation of the sea anemone is caused by the radial muscles contracting and the opposing longitudinal muscles relaxing. In feeding, or when the tide falls, the sea anemone shortens by contracting its longitudinal muscles and relaxing the radial muscles. In both elongation and shortening, the mouth must remain shut to enclose the fluid gut contents and maintain the pressure of the hydrostatic skeleton. These sea anemones, called Cerianthus and here partially exposed, use the fluid inside the gut to transfer the force exerted by the muscles. Radial muscles squeeze the fluid downwards, pushing the body into the sediment. This lower part now acts like an anchor, upon which the longitudinal muscles contract to pull the sea anemone down into the sediment. And so this cycle is repeated. And in the past, as now, the physical environment would have been similar, so we can be sure in inferring that these cnidarian trace fossils testify to a very similar burrowing habit. In fact, these fossils, as I hinted, can tell us more. Look at the gut contents again. These fragments, occupying the form of space of the coelentron, are digested fragments of trilobites, an arthropod. The conclusion is inescapable, then, that even though this sea anemone lived in a burrow, it could successfully trap these active arthropods. Nevertheless, the cnidaria were not the most successful metazoans in exploiting the environment because of their locomotory and other limitations. And we are left with the flowers of the sea, the sedentary coral polyps and other drifting relatives, such as the jellyfish. For further evolutionary advances, we look to the organisms that left these fossils. The impressions of a flatworm, Dickinsonia, with a distinct bilateral symmetry and front end here, They probably fed on bottom detritus and developed the mouth and sense organs at the front end. Many flatworms move by ciliary locomotion, but these Precambrian ones, like the larger flatworms today, must have used more powerful muscular contractions. It's the use of muscles, as against cilia, that allows a really successful exploration of the environment. These flatworms are only about half a centimetre long, but larger ones exist in tropical seas. As flatworms are the most primitive triploblastic animal, we would hope to be able to trace transitions between them and more advanced metazoans. One feature of this transition that is shared by both primitive mollusks and flatworms is the type of muscular locomotion. These are the locomotory waves and muscular contractions sweeping over the surface of the foot of a limpet. And using such muscles, this gastropod is propelled over the wet sand. Look how the trail it has left has been dimpled as the foot has moved over it. And here, look at the number of trails that these winkles leave when we film them in time-lapse. And here are some trace fossils which have been made by mollusks. They are called scalecia. In this slab we can see that they have been meandering across the sediment surface. Their muscular foot ploughing through the sediment. Now, if we look at a slightly smaller slab, we can see additional details within these trace fossils. The incremental movement of the muscular foot is here clearly recorded as a series of serrations along the trace fossil. But you may have noticed a problem. I was talking about furrows pushed into the sediment, yet these trace fossils are preserved in positive relief. How has that happened? If you recall the fossil beach I showed you a little earlier, you will recall that sand was laid on top of the ripples, making a negative cast. Exactly the same thing has happened here. If we look finally at the smallest specimen, we can see that this layer of sand was deposited above the trace fossil. You can see the outline of the original furrow just here, and turning it over, the trace fossil itself. The evolutionary transition from flatworm to mollusks has been envisaged, but how do you get from something like this, a flatworm, to something like this, a lobster, that is an arthropod with jointed limbs? This is Peripatus, which, despite appearances, is an arthropod, in that it is segmented and has other structural features of the blood system and respiration, which are characteristic of all other arthropods. Evolution of the typical arthropod has seen the flexible cuticle hardened into a rigid exoskeleton, and muscles attached to this exoskeleton provide effective levers, that is legs, on which to walk, and which left such traces as these on the floor of some Devonian sea. And modern-day arthropods demonstrate how active and agile this form of locomotion can be. Amongst the trace fossils left by arthropods, those made by trilobites are especially well known. This superb slab made in the University of Oslo in the paleontology department shows both the trilobites and some of the tracks they made. Let's look first at the trilobite itself. It has a head, a middle area, the thorax, and a tail. Anteriorly, there were antennae which sensed the surrounding environment. Now let's go on and look at the cross-section of this trilobite. There is a dorsal exoskeleton, and beneath the exoskeleton there are paired appendages. These, like other arthropods, are jointed, and that means that they're ideal both for scratching and scraping at the sediment. Imagine in this cross-section both appendages coming together. What would happen to the animal? It would sink straight into the sediment, as we can see in this specimen here. Why would a trilobite sink into the sediment? Presumably to escape from predators, but note that the eyes remain above the sediment surface so that they can keep a wary lookout. Underneath the resting trilobite there is of course a trace. The name of this trace, shown here, is Rusophycus. Not only did trilobites make these resting traces, but also walking traces, and as the appendages swept backwards, they produced this very characteristic chevron mark. The name of this walking trace is Cruziana. The resting trace, Rusophycus, and the walking trace, Cruziana, can merge into each other, as in this specimen here. Here is Rusophycus merging into Cruziana, and of course the trilobite at the end of the trail. Trilobites could also swim, and to do this they walked faster and faster across the sediment surface. Lift-off, however, before final swimming was a little uneven. For instance, in this specimen, the posterior spine has trailed along the sediment, leaving a narrow groove. So far, I've been considering movement largely over sediments, and in doing so, looked at some of the transitions from cnidaria, then onto flatworms, and from flatworms onto mollusks and arthropods. Now's the time to look again at burrowing, so let's take one last look at burrows. This slugworm is about to burrow. By expanding the body to form an anchor, it pulls itself into the sand. These alternate contractions are also aided by ridges on the body wall, which are used to push sand aside and to anchor the worm. It is the fluid-filled body cavity, the coelom, together with the antagonistic muscle contractions, which propel the worm through the sand. The use of the fluid-filled coelomic cavity appears to be a most efficient way of transferring the contractile force of the locomotory muscles, and it is thought that it arose primarily as an adaptation for burrowing. The razor shell uses a different fluid-filled cavity, the hemisphere, upon which its muscles act, but the net result is the same. You can see the foot probing into the sand, and once in, it goes through alternating contractions, which dilate the foot to anchor it in the sand, so that other muscles may pull the animal down. Near the beginning of this program, I emphasized how, if we look at trace fossils, we can get some idea of the grade of organization in animals. If we complement these studies of trace fossils with examination of living material, we see, for instance, that both cnidarians and annelids and mollusks burrow. They all use a fluid cavity, but in each case it is different, the coelentron, the coelom, or the hemisphere. This is a classic case of evolutionary convergence. They are using entirely different organs of entirely different origins, but the net result is exactly the same. What about the converse of the evolutionary coin, evolutionary transition between two major groups? Again, trace fossils seem to give some indications of what was going on. Take the transition between platyhelminths and mollusks. The basic locomotory style was almost identical, and by studying trace fossils, we should be able to, one day, trace that transition. However, all these transitions, all the origins of the major phyla, were in the Precambrian. So if we're going to get the paleontological evidence, we must look in Precambrian rocks. There's still a great deal of work to be done, but the search is now on.